Notice which permutation. Definition. So a permutation is an ordered arrangement of all or some of the members of a set. Okay? So usually what we say is in permutations the order matters. Okay, one of the questions you're going to have to ask yourself, not in this particular section, because in this section they're all permutations, but later on when we're doing general questions, you have to ask yourself, does the order matter? Okay? And you have to come up with an answer for that, because if the answer is yes, it's a permutation. If the answer is no, then it's something different, which we'll do. It's a combination. Okay, which we'll do later. Permutation notation. All right, so first off, we can use the fundamental counting principle to determine the number of permutations, in this case, of the letters in the word logarithm, if all the letters are used without repetition, and the permutations, and now we're going to put some restrictions on this thing, right? So, question one, whenever you're doing a permutation with letters, how many letters are in logarithm? 7, 8. So there are 9 letters, right? Okay, so 9 letters. And they're all different, right? So you can imagine that you have 9 Scrabble tiles in front of you, right, with an L, an O, a G, an A, an R, an I, T, H. We say that must begin with an L. So fundamental counting principle, we write down 9 blanks, 3, 4, 5, 6, 8, 9. And when you're doing permutation, you start off with your restriction. So what's the restriction here? First letter has to be an L. So I'm just going to put that underneath there and say, that's an L. How many L's are there? There's 1 L. Okay, how many letters remain to go in second position? 8. And then, and 1. Okay, so we can just multiply that out. Now you'll notice that that is the same as 1 times 8 factorial, right? Which is just 8 factorial, which I have the number. And here's 40,320. Now what we want to get you used to doing is looking at things if it's written from a fundamental counting principle point of view, if it's written using factorials, or if it's written using permutation notation, which we're going to hit a little further down the page. Right? But you might see your answer. The answer might not just be a number, right? It might be an expression. And you have to look at that expression and say, okay, does that match this scenario? Must begin and end with a vowel. Now sometimes fundamental counting principle is just the easiest way to do it. Or the, it's the least stress. It's just like, okay, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I write down my 9 blanks, and I know it's got to begin with a vowel, so I'll put a V there. It's not a V that's, you have to understand context here. It's a vowel. Okay, how many of the letters in logarithm are vowels? Okay, so we've got vowel, vowel, vowel. We got 3. So how many choices do I have for this first blank? 3. How many choices, because we got to deal with restrictions first, so how many choices do I have for that last blank? 2. Okay, we've used up how many letters? Out of? So there are? So how many are left? 7, and then 6, and then 5, 4, 3, 2, 1. Okay, and we can just multiply that out. And you might notice that this also could be written as 3 times 7 factorial times 2. So you're just thinking, okay, first letter is a vowel, I got 3 choices. Then, you might want to leave a blank there, go to the end and just say, well, there's 2 choices for the last one. In between, there's 7 letters, and I don't care about the order, so it's just 7 factorial. And that works out to 30,240. Must have the vowels together. Okay, so we kind of dealt with something along this line, I think, the last period. So we've got an L. We've got the vowels O, A, I, and then we've got the G, the R, the T, and the HMS. Could be like a ship. Okay.
Wait, there is no
There is, oh, it's just logarithm?
Yeah.
Sorry. It's a singular. All right. So then we say, okay, so how many tiles, air quotes around that, how many tiles do I have to arrange? 1, 2, 3, 4, 5, 6, 7. Right? I have 7 tiles. Because the OAI is on 1 tile. This is 1 tile. So 7 tiles can be arranged 7 factorial ways. And you say, but wait, you have 3 letters on that 1 tile. How many ways can they be arranged? 3 factorial ways. So it's 7 factorial times 3 factorial. Okay? So we have 7 objects to arrange. Right? One of those objects is a tile containing OAI. So for each one of those 7 factorial arrangements, it could be OAI, OAI, OIA, IAO, EI, etc. Right? There are 6 ways to arrange those, and that is also 30,240. Now that brings up some interesting thing, right? If this question is asked, and they give you this notation, or they give you this notation, right, then this notation would be more correct, right, would be correct. Now, if you're just working it out and getting 30,204, so, for example, if the answer was written in factorial notation, and you saw this, and you also saw this, you work them out, so you just do it and you say, there's 30,240. I got to see which one of my answers is 30,000, then you got 2 of them. And you're going to say, okay, which one matches the situation? This matches, this is not a 3 factorial, right? There's 3 vowels and then 2 vowels. This matches this situation where I'm arranging those 3 objects. Okay? So just because, if it's given in factorial or permutation notation, we'll call that actually combinatorics notation. Don't just take the first one you work out and say, well, that's the number I got, right? Because there might be more than one that works out to that, and then you'll have to distinguish between them. Cannot have all the vowels together. Okay, so we did stuff like this, right? Yeah. So it's going to be 9 factorial, which is there is no restriction, minus 7 factorial, 3 factorial, C, right? So in other words, to try and do the ones where you can't have the vowels together, there's too many possibilities, right? Okay, you can't, and they can't all be together, right? So now I need to split them up somehow, and you'll be sitting there working your way through about 17 different scenarios and having to add those all up, and you won't get it right. Or we could just say, well, what else could I do? I could take all arrangements, which is 9 factorial, right? That's all the arrangement, and subtract from that the one that do have the vowels together, and then I'll get the ones that don't have all the vowels together, right? And remember, this is cannot have all vowels together. Okay, this works out to 332,640. And a lot of times, the numbers are interesting in a certain sense, but you don't necessarily need them, right? It's just sort of like, yeah, okay, that's the thing. And if I have to work out a number, then I can. All right, use fundamental counting principle. Again, we're using fundamental counting principle to determine the number of permutations of letters in the word factors. If the letters cannot be repeated and the permutation contains only 3 letters. Okay, so how many letters? 7 letters. Okay, now nowhere in here, if it said vowels and stuff, you could count those. At this point, there's no point in counting vowels, right? So it doesn't matter. Okay, if I want 3 letters, so fundamental counting principle, how many blanks? 3 blanks. How many choices do I have for the first letter? 7. How many choices for the second letter? For the third letter? All right, and that's what? 210, right? That's 30 times 7. What if there are 5 letters? Okay, you should be able to write that down, right? Here we go. So how many choices do I have for the first letter? So 12 times 210, 2100, and then 410, 2520 or something? Okay, 2,520. Yeah. If I'm doing a test, I'm actually pulling out the calculator and doing it. Represent the answer in question 2 using factorials. Huh. Okay. Now wait, we kind of did something like this again on the first day, right? So 7 times 6 times 5 is the start of 7 factorial, right? So you'd say, okay, so it's 7 factorial. Now if I wrote that out, I would go 7 times 6 times 5. Now if I want to get rid of everything below 5, I would write 7 times 6 times 5 times 4 factorial and put it over 4 factorial. Okay. So if you think about, well, wait a sec, what's this, right? Well, this is 7 times 6 times 5 times 4. And remember, we can stop a factorial expansion anytime we want simply by putting down the factorial symbol. And you're left with 7 times 6 times 5. Okay. You do the next one. We're using factorial notation. And just figure where you want to stop, right? I need the 3. It's just I don't need the 2. So 7 factorial over 2 factorial. Okay, you might say, well, why are we doing that? I mean, it's interesting, but why? Well, here you go. The number of permutations of n object taken r at a time, so n objects taken, so we had 7 objects taken 3 at a time or 5 at a time, can be determined by, no idea what goes in there. No. So we just saw, right? It's n factorial over, all right, let's back up. So 7 taken 3 at a time gave me 7 factorial over 4 factorial. 7 taken 5 at a time gave me 7 factorial over 2 factorial. So where's this bottom number coming from? So it's 7 minus 3, or 7 minus 5. So it's n minus r factorial. This is NPR. Okay, it's represented by n, capital P, and then an r. It's equal to n factorial over n minus r factorial. It's on your formula sheet. There's an NPR key in your calculator. Okay, in the same place where the factorial symbol is. Okay, it's like number 2 or 3. I think it's number 2. And the factorial symbol is number 4. Where n and r belong to the natural numbers, not quite natural. Actually, it's the whole numbers because you can have 0. Okay, and n is greater than or equal to r. So if you're choosing, you cannot choose 8 objects from a set of 7. Right? That makes no sense. How do I can't do that. Okay, so then n has to be greater than or equal to r. Examples. Evaluate 10 factorial over 6 factorial, 4 factorial. Okay, so we'd say, well, 10 times 9 times 8 times 7 times, when am I going to stop this thing? 6. Do I keep going? No, because I have a 6 factorial on the bottom. Now, there's also a 4 factorial there, right? It's okay. 6 factorials cross off. And 4 factorial is 4 times 3 times 2 times 1. So 4 and 2 give me the 8. Take out an 8, right? And 3 goes into 9 3 times. So we got 10 times 3 times 1 times 7 times 1, or 210. That's not something you're really ever going to have to do, right? Because you can just you could just plug that in your calculator the way it sits. Evaluate 8p5. Okay, so the formula 8p5. 8 is n, so it's n factorial over n minus r factorial, which is 8 factorial over 3 factorial, which would be 8 times 7 times 6 times 5 times 4 times 3 factorial over 3 factorial. And we can multiply those out. But I mean, really, you could use your calculator, right? So to use the NPR, you have to put in n first. So on your calculator, enter an 8. And then go math and over to PRB. Then you want number 2. So go math, PRB 2, and you'll see 8. Depending on your calculator, it might be 8, then a P, and then you put in the 5. Okay, and then hit enter, and it'll evaluate it for you. Okay, and that's equal to 6,720. Okay, so depending on your calculator, you might see 8 NPR 5. Right, that's what Sam sees. Right, and if you have the, we'll get that updated. I saw it, it was hiding behind. And if you have the newer firmware, you'll see a little 8, and then the P, and then you put in the 5, and you hit enter, and you get 6720. Show that 15 factorial minus 13 factorial is equal to 209 factorial. Okay, so we've got 15 factorial minus 13 factorial. So we think about it, let's expand 15 factorial until we get a 13 factorial, right? So 15 factorial is 15 times 14 times 13. Remember, I can stop an expansion anytime. Now, why stop there? Well, they both have a 13 factorial, right? So it's a common factor, yeah? So we can factor it out. So it's 13 factorial, and we've got 15 times 14 minus what? Minus 1. What's 15 times 14 minus 1? Well, 15 times 15 is 225, so it's 15 less. So it's 210 minus 1, which is 209. Okay, so we have shown, hey, look, 15 minus 13 factorial is 209 times 13 factorial. Now, a lot of this is just playing with definition of factorial, right? But it also means that's questions that you could see. And you got to know, okay, how do I handle these particular types of questions? Well, I could just start expanding, right? If in doubt, expand a factorial out. You know where to stop. Okay, we get something common. Determine n if np2 is 56. Now, np2 is n factorial over n minus 2 factorial. And that's equal to 56. Okay, if in doubt, expand it out. Which one is the bigger factorial? What's bigger, n or n minus 2? N, right? We figured that out. It's been 12 years. We know this one. A number is bigger than 2 less than a number. Okay, n times what? Times n minus 1 times what? Times n minus 2 times what? Stop here, right? Why? You get an n minus 2 on the bottom, yeah? Well, not an n minus 2. I get an n minus 2 factorial on the bottom. So what can I do with the n minus 2 factorials? Cross them off. What do I put in their place? The number 1. Just remember there's a 1 there, so you say, oh, look, there's a 1. Okay, so what do we have? N times n minus 1 is 56. So n squared minus n minus 56 will be equal to 0. It's just quadratic. We expand out the left side, n squared minus n. We move the 56 over, which becomes what? N minus 8 and n plus 7. So what's n? N equals 8, or n is equal to negative 7. Now, what do we know about n from our whole definition? It's got to be a whole number, right? Okay, so it has to be greater than, right, it's a number of objects, right? It's the things. We're ranging, we're taking 8 objects. And what we're doing is actually 8p2, and 8p2 is 56. Okay, so you could verify that by going 8p2. You could also try negative 7p2, which your calculator should object to. So you can't do that. All right, along the same lines, algebraically determine n plus 2 p3 is equal to 336. Oh, by the way, you can solve these graphically. Well, okay, graphically is a bit. You could solve these using your graphing calculator. So if they're foolish enough to give you a question that looks like this, which they won't, but here, yeah, close that. Here's what you would do. Because I want to do NP2, let's say. So I'm going to go X, because I don't have an N. Math over to probability 2, NP, XP2. Okay? Now, I don't want to graph that. What I'm going to do is go look in the table and just say, whoop, hang on. Oh, it's got to be in Y equals. My bad. Go to Y equals and put in X, math, over to PRB, XP2 in Y1. Okay, then go to the table and just say I'm looking for 56. There it is, and the X value that's associated, so XP2 56. These teeth dressed up. So the value of X that makes that true is 8, right? So that's a way to check. Or, if it's a multiple choice question, it's a way just to answer without having to do anything beyond that. However, we give you written response questions, right? Like algebraically determine n, if n plus 2. Okay, so we know the definition of NPR. It's the first thing, right? This thing here, that's my n in the formula, right? Even though they use an n. So it's n plus 2 factorial over n minus r factorial. Yep.
We have a different question on
Do you? What's yours?
it's n plus 2 p2 is equal to 100.
N plus 2 P2 is equal to 182. Okay. All right, so let's do a 2 here then. Yeah, just if you see any discrepancies. So n plus 2 factorial is n plus 2 factorial. What's n plus 2 minus 2? Just n, right? And then it's factorial, right? So it's n plus 2 minus 2, which is n factorial. What's bigger, n or n plus 2? N plus 2 is bigger. So what are we going to do? We're going to expand. How do we expand n plus 2 factorial? N plus 2 times n plus 1 times factorial. Those are slow. 30-2s are way better at this stuff. You got to know when to stop, right? And say times n, and you can say factorial. Stop there, right? Because you have one of those on the bottom. Okay, those cross off. You got 1s. So we have n squared plus 3n plus 2 is 182. N squared plus 3n minus 180 is equal to 0. Okay, so expand it. We need a quadratic, so you're going to expand the left side. You're going to move the right side over. Okay, so it's equal to 0. So we can't solve quadratics unless they're equal to 0, right? Okay, so we've got to factor that. Need two numbers to multiply to 180 and differ by 3. So they're going to be close-ish to the square root of 180, which is, I don't know, square root of 180, 15, 14. Sort of 15 and 12 probably. Okay. N plus 15 and minus 12. You should check that because I'm just pulling numbers. Okay. Obviously, I don't have the key to this one. It's not on my sheet. Okay, so n squared 15. So I've got the plus 3n, and then, okay, 10, 150, yeah, it's 180. Okay, so n is 12 or n is negative 15. And what do you got to say about that? Cross off the n is negative 15. It's got to be a whole number. Okay. Remember, n is a number of objects. Okay, which means if we go 14p2 on our calculator, right, because n is 12, it's like a quit right there. Let's see if I go down and edit that down to be a 14. 14. Okay, 14p2 is 182. Graphically, if you did x plus 2, p2, okay, don't graph it, right? Just go into the table. Not the graph. You don't want to graph it. Look for 182, right? And it should be where n is 12, right? Because we're actually looking for n. Okay, and then when n is 12, we get 182. Okay, that's verification. Okay, is the next one the same on your sheet?
Yes.
Okay. All right, so I'm just going to wipe this up. Clear some space. What should you do first? Divide both sides by 2, right? Simplify. Simplify if you can. So we've got NP3 is equal to 60. NP3 by definition is n factorial over n minus 3 factorial is 60. What's bigger, n or n minus 3? N is bigger, okay, so expand the top, stop when you feel you should. But I'm not doing it for you because you guys will never stop me, so you have to stop yourselves this time. Uh-oh, cubic. It's okay, we know how to do cubics, right? Okay, so what have we got? N times, let's do it this way, n and do this. So we got n squared minus 3n plus 2 equals 60. Let's go with that. So n cubed minus 3n squared plus 2n minus 60 is equal to 0. Okay. Okay, give me a 0. So you're just going to graph n squared minus 3n, or n cubed minus 3n squared plus 2n minus 60. I wouldn't spend too much time looking for the 0. Just go into the table, right? Because what do we know about n? Has to be a natural number, right? So there has to be a natural number, or whole number, right? You don't even need to look below 0. What do we get? 6. 5. Sorry, 5. Okay? So we know that 5 works, so we're going to go n minus 5, and we're going to go 1, negative 3, 2, negative 60, so 1. Negative 3 minus 35 is 2, negative 10, that's 12, negative 60, that's 0. So we've got n minus 5, we've got n squared plus 2n plus 12. And that's equal to 0, right? Don't forget that equals 0. So top, there's not a lot of room to squeeze it in there. So we know that n is 5, right? So 5p3 should be 60. Okay. We could work that out. But there might be another value, right? We don't know. We haven't done enough permutations to know, hey, is there another value? So we should try and solve this. Doesn't factor. Let's just do this. B squared minus 4ac is equal to 4 minus 4 times 1 times 12, like negative 44, so there's no solution to this. Okay? It's got a discriminant which is less than 0. There's no solution to that. Okay? If you tried to do it, it would be like negative 2 plus or minus square root of negative 44 over 2. Right? I just worked this out. And the reason I did that is when c is greater than 0, it's pretty likely you don't have, right? If c is greater than 0, this is going to be a minus. We know that b squared is positive. So is 4ac bigger than b squared? In this case, yes. Okay? So, no solution to that. So n equals 5. That's your only solution. Okay? But you need to show there's no solution to this, okay? Right? It's part of, part of your job. You got to say, okay, yeah, n is 5, got that, but I need to say, look, there is no other solution. Okay? Maybe there is another solution. We don't know. But now we do. Okay, any questions on how? Okay, so just set it up. Definition of factorial, right? Expand. Larger number, keep going, right? Factorial, just multiply by the next smaller, next smaller, next smaller, until you get something that's the same. Stop. Cross those off. Cubic. I think that's why they changed the other one. It would have been another cubic, so that's why they decided, no, can't do 2. Use fundamental counting principle to determine the number of permutations of n different. Oh well, here's the say. What's the value of 0 factorial? Okay, so we have to define that, right? Because it's going to come in, and this is what we'll show that here. We'll say, well, look, it's going to come in, and how do we define it? So fundamental counting principle determine the number of permutations of n different objects if all of the n objects are used in the permutation. All right, so we start with n times n minus 1 times n minus 2, but the ending with 3 times 2 times 1, right? Fundamental counting principle just says, I'm going to put down n blanks, and I'm going to multiply n times n minus 1, etc., etc. So what's npn? Well, it's this, right? What's this expression? N times n minus 1 times n minus 2, 2 times 2 times 1. Just n factorial, right? That's just how we write n factorial. Use the formula NPR to determine NPN, right? So in this case, it's n factorial over, now what goes down here? N minus n. What's n minus n? Okay, so NPN, using the formula, works out to n factorial over 0 factorial. But NPN is n factorial, right? So we've got this. NPN is equal to n factorial over 0 factorial. That means that n factorial, this, has to be equal to this. So what's 0 factorial equal to? So if that's equal to that, what are you dividing by? 1. So 0 factorial is defined as 1. Okay, and that's why.
But isn't it 0 times?
No, 0 factorial is defined as 1. Notice the is defined as. Okay, why? So that this will come out true, right? If this is true, we have to define, right? Because you can't say, well, it's the arrangements of 0 objects. It doesn't make any sense. There are no objects, right? So instead we define. Okay, in order to keep this system consistent, we just say, okay, this is going to be the case that we're going to have to define 0 factorial as 1. Calculator functions, so we've looked at those, right? So 9 factorial was started with a 3 and ended with like an 880 or something. What was it? 362? What is it? Don't write that down. I don't have it written here. What's 9 factorial?
Or 316.
You're right.
Is that right?
Yeah. Wow.
It's good. Now I can do 10 factorial. Throw a 0 on the end. Okay, what's 9p4? I'm not writing that one down. I don't even have it written here. You need your calculator for that, right? So 9 NPR 4 equals
3,024.
8,024? Who?
3,000.
3,000. 3024? Use the calculator to evaluate 3 times 5p2. Somebody said 60. Okay. Now, when I learned this stuff, there were no calculators. There were certainly no calculators that would have done permutations or combinations. So we just had to say 5p2 is 5 factorial over 3 factorial, which is just 5 times 4, right? Which is 20 times 3 is 60. Okay. Now, you're saved from having to do that. You don't actually have to use your brain. But I think it's kind of handy if sometimes you can do that, just so you know. And it gives you an idea. Permutations with restrictions. Okay, so this is where we really started, right? Got to begin with an L. Has to end with a, has to begin and end with a consonant. All the vowels can't be together. Those are restrictions. Any of these questions can be done using fundamental counting principle. Okay? And they can be done using permutations. Now you might have a preference. In a small sense, it doesn't matter. Just remember that when you go to look at the answer, it might be written in terms of fundamental counting principle, right? Like 1 times 8 times 7 times 6, etc. It might be written in terms of permutations, right? Like 3 times 5 P2. It might be just the number, 60. Okay. You might work it out a different way and then have to look at the answer and say, well, I use fundamental counting principle, but they use permutations, right? Or vice versa. So we're going to do them, a lot of these we'll do both ways, right? And you just get used to the fact that I can do this more than one way. My answer might look different, okay? It may be in a different form. That doesn't mean it's wrong. If in doubt, I can work my answer out, get a number, and then work out each of A, B, C, D. And if only one of them agrees, then it's like, okay, yeah, that's the one, right? If more than one agrees, then you have to kind of drill a little bit deeper and say, which one of these explains the situation properly or not. And if you'd had that already, you'd already have the answer without having to actually work it out, right? But those are just different strategies. Okay, number of ways the executive committee consisting of a president, vice president, secretary, and treasurer could be selected from a student council consisting of 15 students if there are no further restrictions. Yeah. Okay, so does the order we choose the people matter? Well, they're filling positions, right? So I'm going to say yes, it does. If I was just choosing 4 people to sit on a subcommittee, then I would say, no, it doesn't matter what order, right? It's just like, who cares? In this case, order does. Okay, I have 15 objects, right? I want 4 of them where order matters. How do we express that? In permutations. It's going to be 15P4, right? All the arrangements of 4 objects from a set of 15 where the order matters. Okay, 15P4. If I was using fundamental counting principle, I would say I need 4 people. I have 15 choices for this is president, this is vice president, this is secretary, this is treasurer. So I would say it's 15 times 14 times 13 times 12. Right? I know that 15P4 is 15 factorial over 11 factorial, which is 15 times 14 times 13 times 12. Okay, so they are the same way of expressing. Okay, and I have answers written down here, so I'll give it to you. 32,760. Okay, so top using a permutation, bottom using fundamental counting principle. If I ask you that as a written, either one is acceptable if I don't say use permutations or use combinatorics notation. If I just say how many ways are there. Okay, what if Jerry must be the treasurer?
Who the hell is Jerry?
Somebody that's, we're going to assume Jerry sits on the executive committee.
Well, what if there's 2 people named Jerry?
Okay, we're going to assume there is but one Jerry sitting on the executive committee. It's not an unreasonable assumption to make because they didn't say the older of the 2 Jerrys or the taller of the 2 Jerrys. How many Jerrys are there? We've figured out. There is 1. And how many of them do we need? So we're going to go 1P1. I want all the arrangements of 1 Jerry taken one at a time. What's 1P1 probably equal to? 1. Right? If you're choosing one object from a set of one thing, you can only do that one way. Right? It's like, there's Jerry. How many non-Jerrys are there? And how many of them do we need? Now we know it's a permutation, right? Because we're going to put those people in a president, vice president, secretary. Okay, so how many further people do we need to fill this? 3. So you will notice that these first numbers add to 15. So we are taking into account all 15 people that are on this committee, right, or on the student council. And you'll notice that these second numbers add to 4, which is the number of positions we are choosing. Choosing is a bad word. Number of positions we are figuring out, we are filling. What's another way to do that? Well, president, vice president, secretary, treasurer. It's our restriction, right? How many ways do we have of choosing the treasurer? 1. When you're doing fundamental accounting principle like this, you have to deal with the restrictions first. We got to take jury, we got to stick them in there. How many people are left for president? Okay, so 14, 13, 12. Okay. Which is equal to 2,184, both of these, right? 2,184. So you got to start getting the mindset of figuring out, does order matter, which is a permutation, or not, which is called a combination, but we'll get into later. Right? This is not on the test Wednesday, right? Test Wednesday goes up to fundamental accounting, but here's some fundamental accounting principle stuff, right? So, although permutation notation isn't, this question could be. Right? There's nothing wrong with this. It could be done using fundamental accounting principle. If on multiple choice, if you're given fundamental accounting principle, you can use permutations. Nobody's going to know or care, right? Although you should write it out, because we should both know what you did, but I don't care. And if you, unless it specifically says solve using the fundamental accounting principle, if you're solving something you want to use permutations, feel free. Okay? As long as it says algebraically determine. Okay? If you choose to use permutations and they are applicable, that's fine. Okay? If it says use the fundamental accounting principle to algebraically, then you got to show fundamental accounting principle. Okay? Melissa must either be the president or the vice president. All right, what do we have to figure out then? Number of ways that Melissa could be the president, which is really the same number of ways that Jerry can be the treasurer, right? Just we're choosing one person for a specific position. So it'd be 1P1 times 14P3. So 1P1 times 14P3. Now, what's this first one? What are we doing? Figuring out the number of ways Melissa can be the president. Or, what does the word or translate to as a mathematical operation? Plus. So, and, right, Melissa is president, and we choose 3 other people from the 14, or not choose, but we. Or, Melissa's the vice president, and we choose 14P3. No, I would multiply it by 2. If you squared it, I'd probably put the answer there, but you'd get it wrong, right? Because it's a plus. So all you gotta do is take your answer from B and double it, right? So it's 4,300. It ends in an 8, and it's got a 6, and then that's a 3. 4368. Methane. Or, because you could do this using fundamental accounting principle. President, vice president, secretary, treasurer, or president, vice president. So P, VP, ST, P, VP, ST. So we're going to make her the president. And then we have 14, 13, 12, or, which is plus, we're going to make her the vice president, and then we've got 14, 13, 12. Okay. Which either way works out to 2 times 14 times 13 times 12. Try not to put 1P1 in your calculator. It's just sort of bad form. So you should know that's a 1. Right? So it's really just 14P3. Knowing that, you should really not do 14P3 plus 14P3. You should really just go, oh, it's like 2 times 14. But it's fine, right? I mean, if you do it with the plus, it means it's going to take you seconds longer to do it that way, but it's not that many seconds. Okay. So any question on the executive committee to the executive committee? Or sorry, the student council to the executive. The license plates for one particular state consist of 2 letters followed by 5 digits. Determine the number of license plates that have no repeating letters or digits. Now, me, I like to do fundamental counting principle, right? It's pretty no-brainer, right? You just put down blanks and you fill them in. So I'm going to start with that. License plate consists of 2 letters, so letter, letter, and 5 digits. 2, 3, 4, 5. Okay, so I have to do, if I'm going to do fundamental counting principle, I have to put down 2 blanks for letters followed by 5 blanks, right? And it's letter and number, and that's the times, right? So, no repeating letters or digits. How many choices do I have for the first letter?
26.
26. How many choices for the second letter? 25. How many choices for the first digit? 10. You are allowed to put a 0 in here, right? It's not, because we're not making a numeral, we're just saying digits. Second digit? Third? Okay. Now, from this, I can now figure out the permutations, right? Which maybe some of you could have figured out. So, okay, look, there's 26 letters and I need 2 of them. I need all the arrangements of 2 letters from a set of 26, which is 26p2. And I need all the arrangements of what? 4 digits from a set of 10. So it's really just 26p2 times 10p4. And if you can figure that out to begin with, that's great. Right? Because again, the answer might be written as 26p2 times 10p4. It might be written as 26 times 25 times blah, 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 blah. It might be written as, what does this actually work out to? 656. Or express that another way, a lot. A lot of different license plates you can make. Now we know, of course, that they do taste. There's certain letters that aren't allowed on license plates, like O and I, because they could be mistaken for a 0 or a 1. Okay, unless you're getting personalized plates, and then you're allowed the O and the I. There are certain combinations of letters not allowed for personalized plates because they are not acceptable words in polite society.
10 or 5.
How many? You're right. It'd be 10p5. See, that's why I do it this way. I can't mess up. Yeah, thanks for that. A little sooner next time. Come on, man. Be on the ball. Okay, everybody good with that one? Yep. Not moving too fast? 5 people get on a bus with 12 available seats. Determine the number of different arrangements of the 5 people if all 5 people take a seat on the bus. So, what do you think? What would you write? Let's reverse those because the first number's got to be bigger. So just 12p5, right? I just need all the arrangement. Does it matter that they're sitting on a bus? No. But they are sitting in a place that I can distinguish, right? I can tell the front left seat from the back right seat. I can tell the front left from the middle left. Okay? So it's just 12p5. And using fundamental counting principle, it's just 12, 11, 10, 9, 8, 1, 2, 3, 4, 5. Right? And I don't even care what that's equal to. Like, it's a number and it's very easily worked out on your calculator. Okay, what's it equal to? 95040. Yes. If in doubt, it's the English alphabet. If the license plates were on Hawaii, it could be the Hawaiian alphabet, which has fewer letters. But on Hawaii, you don't need that many license plate combinations, right? Determine the. So what you're asking when the 5 people take the seat on the bus is, can I tell where they're sitting apart? You know, and yeah, I can, right? I mean, if Joe is sitting in the front left seat and Bill is in the back right seat, that's different from if they're in different positions, right? In the other position. Determine the number of permutations made using 5 letters from equation. How many letters? 8 letters, right? Okay, they got to begin with an E. So here's how I think of these guys, right? It's got to begin with an E. You got these 8 letters sitting on your little Scrabble thing. What do you do with the E? You take it, you put it in first place, or you take it and you throw it out. Right? It's like, who cares about the E, right? It's gone. We know where it's got to go. What's left? 7 letters. Okay? How many do we need? 4, because we already got the E, right? So it's just 7P4. Okay, you want to get fancy? I want my E. Then it's 1P1. Okay, so I need 1E times 7P4. Okay, I need my E, and it's got to be in first place. Fundamental counting principle, 1 times 7 times 6 times 5 times 4. Okay, that's got to be an E. And what's that equal to? 840? Okay. Begin and end with a consonant. At this point, I like fundamental counting principle, right? 'Cause I don't have to think. 1, 2, 3, 4, 5. Consonant, consonant. How many consonants? How many vowels? Who's a vowel? A, E, O, R. Yeah, it's got like all 5 vowels in that word. How many? Can't be a lot of words that have all 5 vowels. So how many consonants are there? So there are 3 consonants for here. How many consonants are left to go here? 2. Okay. How many? So after that, do these all have to be vowels? No, right? So we're done. We've used up 2 out of 8 letters. How many letters remain? 6, then 5, then 4. Okay? Now, as a permutation then, we could think about, well, 3 times 2, right? You need 2 vowels from a set of 3, right? So 3P2. Or sorry, 2 consonants. Sorry, 2 consonants from a set. There are 3 consonants and I need 2 of them. Okay? It doesn't really matter where they go, but they are going in a specific spot. So I've got to do that first. And then I have 6 letters left. But how many of them do I need? 3. What are the first? No, don't do that. So the 2 and the 3, that's 5 letters that I'm placing, right? Okay. Okay. So 3P2 times 6, and what is that? 30, 120, 240, 720? Too lazy to go look at the sheet. Contain an O. Contain an O. What's easier than contains an O? Doesn't contain an O. So we could take all the arrangements. What's all the arrangements? So if we were doing this without restriction, just 5 letters from a set of 8. So 8P5, right? That's all the arrangements. 8P5 minus, okay, how many 5-letter arrangements don't contain an O? Right? Because we want all the arrangements minus the ones that do contain an O. Well, so do contain an O, so let's put the O in there, right? 1P1. How many letters are left? 7. How many of them do we need? So 7P4. So 8P5 minus, now you could, and a lot of times, if you see this written, it may just be written as 7P4, not 1P1, 7P4. So you just have to realize, why are they writing 7P4? Oh, because they already took the O and now they need 4 letters from the remaining 7. Okay? So this is the way that you do this one, right? You do 8P5 minus 1P1, 7P4, or...
Mr. Janover, I think you
did I mess up?
it should be 7P5, I believe.
So,
Because it's all the ones minus the ones that don't contain an O.
Don't contain an
Seven
O.
letters for 5 slots.
Oh, right. Don't contain an O. Right. Do not have an O. Okay, so there are 7 non-O letters of whom yeah, that makes more sense. What's that work out to? 4,200. So I did the ones that do contain an O, but that's not the. Could you do the ones that contain an O? You could say, well, I want 1P1. Let's squeeze that. Okay, I want the O, and then I want 7P4. But that O can go in any one of the 5 places, so then we'll multiply by 5. So you could do 1P1, let's get the O, 7P4, let's get 4 letters from the remaining to build up the 5 letters, but then that O can go in any one of 5 places, so multiply by 5.
Oh, yeah.
Okay, it could go first or second or third or fourth. Okay. Contain the letters chun in that order. Okay, so here's the way that you do these types of problems. It's got to contain letters, got to be in that order. So you say, okay, I need a T, an I, an O, and an N in that order, but they don't have to be together, right? Didn't say that they have to be one block of letters. Okay, so it contains those. We want 5 letters, right? We've got 4, so we just say, okay, look, you can put the letter here, or here, or here, or here, or here. Right? So that one remaining letter, which could be chosen how many ways? So how many letters are left? There's 8 letters.
Yeah.
We've used 4 of them, so there are 4 letters left. Okay, and they can go in 1, 2, 3, 4, 5 positions. Right? So it's 5 times 4, which is 20. Okay? So there are 4 ways to choose the remaining letter, and it can go in any one of 5 spots. Okay, 5 times 4, 20. Make sense? So put those letters down. There's a lot of arrangements that kind of work along these lines if I need stuff in a particular order, but just because they're in order doesn't mean they're together. Right? It doesn't say in order. If they were together, it'd be really easy. It'd just be 5 ways, right? Because you just pick 4 letters. Well, let's see. No, 8 ways. You'd have 4 other letters that could go in the front or could go in the back. That would be it. The final score in a baseball game was 8-5. Determine the number of different scores that were possible after the 4th inning. Okay, so let's say we got Team A and Team B. And Team A is going to score 8 runs. After the 4th inning, how many runs might they have scored? Could they have scored no runs? Final score is 8-5. We're just in the middle of the game. Could you have no runs in the middle of the game? Yeah. Why not? Just says final score. Right? What does the score start as in the game? 0-0. Can you still have 0 runs after 4 innings? Yeah. Could they have all 8 of their runs after 4 innings? So they could have how many runs? They could have no runs, or 1, or 2, or 3, or 4, or 5, or 6, or 7, or 8. Right? We know they're going to end up with 8 runs. We know they started with 0. They could still have 0 runs. Maybe they're going to score them all in the bottom of the ninth. What could B have? 0, 1, 2, 3, 4, or 5. Right? Maybe they've scored none of their runs. Maybe they've scored all of their runs. Okay. So, how many scores are there for Team A? 9. How many scores for Team B? 6. So after the 4th inning, could be any one of 54 different scores, anywhere from 0-0 to 8-5, right? For each of these numbers that A has, there are 6 possibilities for B, right? And there are 9 possibilities for A. So for each of the 9 possible scores for A, there are 6 possible scores for B. 9 times 6. Okay, 54. Make sense? Right. So just say, in the middle of the game, you could have scored all your runs, you could have scored none of your runs. Same for the other team. A photo of the 4 men and 5 women of the math department is to be taken for the yearbook. This applies to any arrangement type of question along these lines, right? Determine the number of different versions of the yearbook photo that are possible if the members are to be arranged in 2 rows. Okay, so 5 people in front, 4 in the back. And there are no other restrictions. So how many ways could you do it if there are no other restrictions? So you have to have 5 in the front, 4 in the back. Okay, let me ask you this. Does it matter if there are 5 in the front and 4 in the back, or 4 in the front and 5 in the back? Does it matter if they're all lined up in a single row? If there are no restrictions? So does it matter? 5 here, 4 here, 4 here, 5 there, 9 in a row? Are any of those different?
Yeah, it says 5 in the front row.
Yeah.
Okay. So 1, 2, 3. What do we got? 5 in the front, rear. Okay. There's 9 people. How many people do I have to choose from for that first front position? 9. For the second front position? What's this looking like? Looks like 9 factorial. How many ways can you arrange 9 people in a straight line? 9 factorial ways. How many ways can you arrange them if there are 5 in the back and 4 in the front? 9 factorial. How many ways can you arrange them if there are 5 in the front or 5 in the back and 4 in the front? 9 factorial. How many ways can you do if there are 6 here and 3? It doesn't matter, right? If there are no restrictions, it doesn't matter. Okay? Because all you've got is, I have 9 different spots. Whether they're 5 and 4, 6 and 3, 7 and 2, all 9, and it makes absolutely no difference, right? So the answer is 9p9 or 9 factorial. Okay? ... 9 factorial or 9p9, which we know is 362,880. Okay. Yeah.
No, give me 9p4 times 9p5 because the people that are
Well, you can't do 9p5 times 9p4. You already have 5 people gone. You have to go 9p5 times 4 people. Right? Which would work out the same. What if the men must be in the back row?
4.
The men must be in the back row. How many positions in the back row? 4. How many ways are there of arranging the 4 men in the 4 positions? So we're going to have 4p4. For each one of those, how many positions are in the front row? 5. How many people are there to go in those 5 positions? So what is it? 5p5. It's okay. Now it matters, right? Back row, front row are now actually different, right? There's only 4 people in the back row, and it has to be 4 specific people, right? Order matters because we can tell the difference if it's, Mr. Italic on one end or me on one end. That's distinguishable, right? So in other words, you'll see for permutation is distinguishable arrangements, meaning you can tell them apart. Okay, distinguishable. Ms. McKay, the learning leader, must be in the center of the front row. Okay, now, we no longer have the men, right? So this is not building on it. It's not like, well, the men and the women have to be here and then Ms. McKay. This is totally separate question. Okay, so treat it totally separately. So if McKay has to be, how many McKays are there? And how many places can she go in? And how many people are left? And where can they go? So it's just 8p8 or 8 factorial, right? Which is, what's 8 factorial? 40,320? I cheated because I just took 8 times 7 factorial, which I actually know. Okay, so 1p1 times 8p8, right? Place the McKay. After that, you have 8 positions remaining. Does it matter that they're in rows? No. Could they be in a line? Sure. Could you be in the center of 9? Yep. Could you be on the left end? Yep. Right end? Yep. They're all 40,320 ways, right? All we're saying is she's in a specific position. After that, there's no restriction, right? There are 8 people left to go in 8 positions. Permutations with identical objects, repetition. Did I miss one?
I don't want to do it.
Wow. Okay. I thought we could finish now. Okay, we can't finish. Determine, we'll get as far as the end of this page. Determine the number of different 3-digit numerals that can be made using the digits 0, 1. Okay, how many digits are there? 1, 2, 3, 4, 5, 6. We have 6 digits. We want to make a 3-digit numeral. There's no further restriction. Okay? If I'm doing numbers, I'm doing fundamental counting principle. Okay, what's the restriction on any numeral question? First one can't be 0. How many non-zero digits are there to go in the first place? 5, right? Okay, how many digits are left? There are 5 left now, right? So we have 6 digits. 6 digits, right? One of them is 0, we take it out. We've got 5 that could go in first place. Okay, this one's gone. We bring the 0 back in now, right? So there's still 5, and that's equal to 100. What if they have to be odd? So what makes a number odd? It's not even. No, okay, it ends in an odd number. How many odd numbers do we have? 1, 3, 5, 7. So there are 4 odd digits. So this has to be odd, and there are 4 ways. Okay, so I have 6 digits. We've taken out an odd one. There are 5 remaining. How many of them can go in first place? Not 0, so there's 4. Okay? Right? Not 0. So the last one's got to be odd. There are 4 digits. We choose one of them. Boom. We're down to 5 digits. One of those is a 0, so we can't put it in. Okay, we've used 2 of the digits. How many go in here? 4. 64. Even. How many even? It's already done for you. Just got to do a slight calculation. 100 minus 64, right? We got 100 total, right? No restriction. 64 of them are odd, so 36 of them are even, right? 100 minus 64. Or, those of you that have nothing but time on tests, right? Bored, you're supposed to, I'm going to go back, try this another way. Say, okay, I got 3 digits. Now we know this is even, but not equal to 0, so that's a 2. So there's one way. Okay, now I've used up the 2. I now have 5 digits left, but one of them is a 0, so it can't be 0. That's 4, and then I have 4. So that's 16. And then we say this is the 0. So there's one way that that's a 0. Okay, then 1's gone. There's no restrictions now, right? Because the 0 is taken up. So there are 5 digits that can go here, and then 4, which is 20. We got to add those together, right? Because its last digit is 2 or last digit is 0. Okay, don't do this. It's like it's easier to do those 2 and get them right than to do this, because something will happen. Multiples of 5. What's a multiple of 5? It's got to end in what? 0 or 5, right? So multiple of 5 means divisible by 5. Any number ending in 0 or 5. Which means we really do have to do 2 this time, right? We have to do ends in 5 or ends in 0. Okay. There's no other way to do this, not like odds and evens or stuff like that, right? So it's ends in 5, so 1, 2, 3. This is a 5. This is a 0. Okay, how many 5s are there? 1. How many non-zero numbers are left to go in first place? 4. And then how many of the 6 having used 2? There will be 4, so that's 16. How many zeros are there? Okay, how many digits can go in first place? 5, because we used the 0, right? So 5 times 4. And it's amazing that this is also equal to 36. Greater than 500. So if you're greater than 500, in our particular scenario, what's your first digit? It's got to be 7 or 5. It's got to be a 5, because we can't make 500, right? whatever number we do has to be bigger, right? Like 501 is the smallest number we can make because we can't repeat digits. So greater than 500, 3 blanks. Okay, this is 5 or 7, so there's 2 of them. 0 is not a restriction in any way, shape, or form now, right? Okay, how many letters or how many numbers are left that can go here? 5 and then 4, right? Because there's 6 numbers. Originally there's 6 numbers. We have a choice of 2 for the first digit, right? It can be a 5 or a 7. Take one of those out, we have 5 digits left. There's no restrictions. So that is 40. Less than 200.
Of course, number can be.
So the first digit has to be a 1. Yeah, can't be 0, right? First digit has to be a 1. 1, there's only 1, 1, and then 5, 4, 20. Okay, 20 ones. Whoa. Oh, wait, multiple choice. Woohoo, you just have to pick an answer.
Can we go into, like, if it said in the question, like, if it said that the digits could repeat, would it just be like 5 times 6 times 6?
Yes. Generally speaking, we do non-repeating, but yeah. If it said repeating, then your only restriction is first number can't be 0. That's 5 of them. After that, you can take any zeros are back in, as are all the digits. Okay, 4 choices. 10 acrobats stack themselves into a human pyramid. Bottom row has 4 people. Next row has 3, etc. Number of different human pyramids that can be formed. So, what is it? Does it matter if they're 4, 3, etc., or if they're all in a row? Or so how many ways can we arrange these 10 acrobats? 10 factorial ways. Okay? If you want, you could sit down and do... You could draw out the pyramid, right? And at some point you would see that, okay, it's just 10 times 9 times 8 times 7 times 6 times, right? Doesn't matter. If you're filling it from here, 10, 9, 8, etc. The answers to a numerical response question is comprised of 4 digits that is to be recorded in a horizontal table of 4 cells. Number of different possible answers. Okay, can you repeat numerical response?
Yes.
Yes. Okay, what's the answer? A, yeah, 10p1, so I need one number from a set of 10 times one number from a set of 10. It's really just 10 to the 4th, right? 10 times 10 times 10 times 10. This is not 10 times 10 times 10 times 10. This is not 10 times 10. This is not. Okay. So, a lot of times multiple choice can be done under process of elimination, right? Just, yeah, what isn't it? Okay, so we will pick up here tomorrow and finish it off.